Next, we have Dr. Amarnath Hegde. He is an assistant professor in the Department of Civil and Environmental Engineering at IIT Patna. He has obtained his PhD from IISc at Bangalore in 2015. Previously, Dr. Hegde has held the short-term research position at the University of Milan in Italy, UPC Barcelona Technology in Spain, and NUS in Singapore, where I'm from right now. So before his PhD, he has also worked as a geotechnical engineer in Keller Ground Engineering India Private Limited in Mumbai for 2 years. He has published 2 books and more than 50 research papers in well-known journals and conferences. He's a life member of several professional the organizations, including ASC, ISSMGE, IGS, ISCT, etc. He is a member of the Technical Committee on Reinforced Field TC218 of the ISSMGE, which is a very prestigious and a very well-known technical committee. He's also a technical committee on geosynthetics of Geo Institute of ASCE from the US. So let's welcome Prof. Hegde to deliver his keynote.
Yeah, thank you. Okay. Yes, good evening to one and all. Firstly, Dr. Shion, thank you very much for the very nice introduction. And I also would like to thank Dr. Shivalsa Kolatyar and entire his team for giving me this opportunity to be part of this nicely themed conference on disaster risk reduction with a special focus on civil engineering aspect. So it's my pleasure and privilege to be part of this wonderful virtual conference. So generally, whenever we hear about the term disaster, generally the natural disaster like earthquakes, landslides, or cyclones, these kind of disasters generally comes to our mind. So I'm going to talk a slightly different type of disaster, which is a man-made disaster. Okay, I'm going to talk about the disaster due to the vibrations. Okay, so vibrations are basically causes the failure of the buildings. It can lead to a cracking of the building, and also it can lead to a failure of the structures. So I'm going to talk about a novel technique which we are trying to develop here at IIT Patna for reducing the intensity of this kind of vibrations and also to protect the buildings and structures from the ground-borne vibrations. So what I do is that before moving to the technical aspect of my presentation, would like to convey best wishes from my institute, which is IIT Patna. And IIT Patna is basically located in the city of Patna, which is capital city of the state Bihar in India. And our campus is almost 500 acres in size, and we have a very beautiful campus. And our campus is very near to the holy river Ganga. And I take this opportunity to all of you from the different parts of the world, different parts of the India. Please do visit our campus if you are visiting this part of the country. So this is how I plan my presentation. Basically, what I do is that I'm going to talk briefly about the different sources of vibration and how these vibrations will create failure or the disasters in the larger term, and how to isolate this kind of vibration, what are the existing strategies, and also would like to share the new methodology we are trying to develop, which is basically a cost-effective way of isolating these vibrations with the help of some field experiments and also 3D numerical studies. And finally, I'll try to summarize our research findings. Sorry. Okay. So vibrations are very common nowadays. It can be generated from the various construction activities. It can also generate from the movement of the vehicles or from the trains or the vehicles. It can also generate from the industrial structures, from the machine foundations. So from the vibration source, typically these vibrations will travel along the ground surface as a surface wave, specifically as a Rayleigh wave, and these waves can damage the nearby structures. As long as these vibrations are within certain permissible limits, buildings will be performing. Else, it will lead to a failure of the buildings, it will lead to a cracking, and in the larger term, it will cause some amount of disasters. So surface waves can be extremely dangerous, but some part of the vibration will also travel along the deeper stratum as a body waves, but these waves are not so harmful. But the Rayleigh waves or the surface waves will generally causes the failure due to this kind of vibrations. And these are some of the photographs which I have taken during one of my site visits nearby Patna. And this particular building is very near to the main railway track, Delhi-Kolkata railway track. And due to its frequent movement of the trains, we can see a lot of cracks in the building. So these all sort of cracks in the structure, in the floor, everywhere. And this kind of cracks can lead to a disaster. It can lead to a failure of these kind of buildings. So each countries basically have their own guidelines for these vibrations, and they have developed their own threshold values. And below this threshold value, if the vibration is there, then there is no harm to the building. But the instance the vibration exceeds a particular limit, then the buildings can be subjected to some amount of risk. So generally, these vibrations are measured by a unit called, or by a parameter called peak particle velocity, which is nothing but velocity of the particle due to the vibration. Okay, under the vibration, particles will vibrate. That velocity, if you measure in a 3 orthogonal direction, and if you take the average, it gives a peak particle velocity. And different countries or different standard codes have their own guideline, be it via AASHTO, British standard, or German standard, or Swiss standard. All these have their own guidelines for the threshold value of the vibration. Okay, so these vibrations are categorized into sensitive buildings, then domestic buildings, and the industrial structure. It also depends on the frequency of the incoming vibration. So frequency of the vibration again depends on the source of the vibration. If it's a railway vibration, the frequency will be somewhat different. If it is a machine foundation, the frequency will be different. But as long as these vibrations are within these permissible limits, then there is no problem as such to the buildings. Instance, it will exceed this particular threshold, then it can lead to the cracking in the building. So whenever it exceeds this kind of threshold limits, the isolation aspect comes into picture. So isolation, in the sense, it is nothing but reducing the intensity of the vibration or protect the structure from the incoming vibrations. So if you look into the literature, there are various isolation methods are being followed all over the world. So most popular one is wave barriers, in which we create some sort of open and infill trenches for isolating the buildings from the vibrations. If it is a machine type of loading, then we can go for absorbing systems like springs or rubber coil systems. Else, we can also strengthen the ground using any one of this method for altering the incoming waves. So the most popular one is basically these wave barriers, open trenches or the infill trenches. So in this trench system, how it will operate is that, so this is basically a source of vibration, and we will basically create a shallow trenches near to this source of vibration. So since the vibration waves are basically a surface waves, these shallow trenches will create some sort of obstruction for the coming waves. So hence it will reduce the intensity of the vibration. So these trenches can be open trenches, or it can also be infill trenches. We can fill some absorbing material here. So if the trenches are placed near to the source of vibration, we call it as active isolation system. If the trench is placed near to the structure to be protected, then we call it as passive isolation system. This particular system is relatively effective and good efficiency in isolating the vibrations, but only the concern is that the depth of these trenches. Generally, the depth of the trench varies from 3 to 4 meter. Okay, if you consider a scenario in an urban area or a soft soil where creating a trench of 3 to 4 meter deep is extremely challenging, because due to safety concerns or due to environmental issues or also due to stability aspect. So in those cases, we also feel sometimes with the infill soil, and this will slightly increase the stability, but the efficiency wise, it will not improve that much. So because of this, all these limitations, what we are trying to propose is that we're trying to develop some sort of a new sort of a isolation system, which can be placed just below the vibration source. I can say it as an active isolation system, because which is placed exactly below the vibration source, and which is made up of material called geosynthetics, which is a polymeric material. And we are proposing to use material like geocells or the biaxial geogrids to be part of this vibration isolation barrier, such that which can absorb some amount of vibration. These geosynthetics are popularly used for increasing the bearing capacity of the soil or reducing the settlement. If they can absorb some amount of vibration as well, it will be a manifold benefits, I can say, bearing capacity wise, settlement wise, and also isolation of the vibration. So we can place this kind of material below machine foundation, below railway tracks, below the pavement. All these are major sources of vibration. And the reason for which we have gone for this geosynthetic material, because these are economical, and main thing is economical. We wanted to develop some sort of a cost-effective isolation system, and it facilitates easy construction. These are extremely durable and resistant to extreme weather conditions, and no heavy machineries or specialized skill power or the labor force is required to construct these geosynthetic structures. So because of all these advantages, we thought of using this material for developing a isolation system which can absorb the vibration. So these are the two materials I'm going to talk about. One is biaxial geogrid, which is a planar type of geosynthetic material, and the other one is three-dimensional type of geosynthetic material. We call it as geocell. In case of geocell, we fill this geocell pocket with some sort of granular materials, geomaterial like soil or sand, okay, which will help us to basically this geocell will apply all-round confinement to the soil, and overall it will improve the performance. In case of the biaxial geogrid, it will basically also improve the lateral confinement on the soil by virtue of frictional and passive resistance. So whenever we use this kind of material, it will basically generate some friction between the soil and the geosynthetics. We call it as frictional resistance. Also, these ribs will try to confine the soil, the movement of the soil. So by virtue of that, both these materials are known for applying the lateral confinement to the soil, and by virtue of that, they improve the performance of the soil. So now I enter into our experimental investigation. I can say it's a field experiments, field vibration test we have conducted just to demonstrate that this geosynthetic based isolation system can absorb the vibration and able to increase the isolation efficiency of the foundation beds. So in this experimental setup, initially we construct a foundation bed made up of geosynthetics, and above that we place artificial source of vibration using this mechanical oscillator. This oscillator can vibrate in a different frequency ranging from 5 Hz to almost 50 Hz frequency, and which is connected to a DC motor which will help us to change the frequency. And under this particular vibration, what we have done is that we have recorded the vibration along this ground surface. Okay, exactly below this vibration source, we have a reinforced foundation bed to a depth of almost 1.2 meter, and using the accelerometers, geophones, and also vibration meters, we try to record various parameters like acceleration, displacement, and all those parameters on a real-time basis. using this particular computer, we have captured all this data on a real-time basis under the source of this particular vibration. And this is how the setup looks like. It is a very tedious experiment, I can say. Initially, we have to create a trench and develop this trench using geosynthetic foundation bed. Then we have to use various sensors on a real-time basis to capture all these physical parameters. And in order to demonstrate this low-cost protection system or the isolation system, we have considered 4 cases, which I'm going to discuss only 4 cases. It's only a part of our research. And initially, we have taken a normal foundation bed. There is no geosynthetics in which. And in the second case, we have used geogrid, which is a planar type of geosynthetics below the vibration source. And in the third case, we have used a secondary geogrid layer below the primary layer, just to see the effect of this secondary layer on the primary layer and the overall vibration isolation efficiency. And in the final case, we have considered a 3-dimensional geosynthetic product, which is geocell. And we have also tried to fill this geocell with different infill condition in the field. So I want to show some photos of how we created a test bed. Okay, initially this kind of trench, we have to dig it up in the soil. Then we have to place the geosynthetics in layer. If you're going for more than one layer, we have to properly compact it, maintain the uniform density and the moisture content throughout the bed in order to maintain that uniform density. This is for the geogrid reinforced case. This one is for geocell reinforced case. We can see we are filling with some sort of a local infill soil, as part of this geocell soil. Then I can say that I don't want to get too much details into the material properties, what we have used, but I can say that this geocell, we used neolloy based geocell, which is nothing but a commercial name of the geocell, and a biaxial geogrid made up of polyester were used as part of the isolation system. So this is a type of vibration load which were applied on the reinforced foundation bed. So if you look into the load, this load was varied from the frequency 5 Hz to 45 Hz. And each frequency, basically what it indicates is that it basically simulates the dynamic force of different magnitude. So we can change the magnitude of the dynamic force by either changing the frequency, or there is something called eccentric setting, because we are applying some sort of a rotating type of force. And using this equation, we can calculate the amount of dynamic force we are applying on the reinforced foundation bed. And I want to show some interesting results. So here, when we change the frequency of the vibration, we also initially tried to record the displacement of the concrete block, which was used to support this particular vibration source. And with the increase in the frequency, at a particular frequency, suddenly the displacement basically got increased. In all the cases, this increase in the displacement can be seen. This is for unreinforced, single layer geogrid, 2-layer geogrid, and geocell. So this particular condition, we call it as resonance. In the resonance, what happens is that the frequency of the vibration basically matches with the natural frequency of the soil foundation system. Okay, and under this thing, suddenly the displacement shoots up. If you consider 4 different cases here, so due to the provision of the geosynthetics, we can see there is a drastic reduction in the displacement during the resonance. Okay, when we place the geocell reinforcement, with the displacement even under the resonance was within the permissible limit provided by the Indian standard. So from here onward, whatever the parameter I compare, like peak particle velocity, all those things, all are compared corresponding to this resonance condition, because it makes sense to compare all this parameter or the different reinforced bed under the resonance condition, because at that instance, the displacement will be maximum. So we tried to measure the peak particle velocity again on the reinforced foundation bed on the surface. we could only measure up to 2.5 meters because it's a field experiment we have conducted. And here, peak particle velocity, again, I told that, it's a unit, or it's used to measure the intensity of the vibration. So 4 different cases we have compared here. One is unreinforced case, single layer geogrid, 2-layer geogrid, and the geocell reinforced case. Here we can see, if you compare this first case and the last case, there is a drastic, reduction in the intensity of vibration or in the peak particle velocity. So if you calculate percentage-wise, it's almost 50% reduction in the peak particle velocity was noted in the presence of geocell reinforced condition. Even geogrid reinforced case provided the reduction in the peak particle velocity. And this gives us a lot of glimpses that these materials can able to somehow absorb the vibration or reduce the intensity of the vibration just below the vibration source. Then we also calculated basically the displacement on the reinforced soil bed, and we have calculated in terms of percentage reduction in the displacement. We call this term as PRD, which is nothing but the difference between the displacement of the unreinforced bed to the reinforced bed. And if you take the ratio of the unreinforced bed, we get this particular ratio, which just gives us how much displacement of the reinforced bed reduces under this particular reinforced condition. So here also, if you compare different cases, with the unreinforced case, obviously the geocell reinforced case yielded us the maximum reduction in the displacement of the reinforced foundation bed. Almost more than 50% reduction in the PRDA was observed in the presence of geocells. Next, what we did is that we calculated the isolation efficiency of different cases, different reinforced conditions. So this isolation efficiency is basically calculated using this particular simple equation, where ARF is nothing but it is a ratio of displacement of a reinforced foundation bed to the displacement of the unreinforced foundation bed at a particular frequency and particular eccentric setting. And here we have compared the isolation efficiency for different cases, again, which is plotted with the distance. So I want to take your attention to this particular line where it is for geocell reinforced case. Here the efficiency of almost 70% was noted. So 70% improvement in the isolation efficiency as compared to the unreinforced bed was observed in the presence of geocell reinforced case. So this is a very good sign, but experimental investigation could not give us the mechanism why this isolation happens by providing this kind of materials, which can only help us to quantify, okay, this much times the vibration efficiency can take place. If you want to develop some sort of a mechanism, then we have no option. We have to go for 3-dimensional numerical modeling, because first of all, these field tests were extremely tedious. And secondly, we cannot see the distributions of stresses and strain in case of experimental studies. So for that case, we have also developed 3-dimensional numerical models just to find out the mechanism why this kind of isolation happens. And for that, we have taken 4 different cases again, as I discussed in the experimental condition: unreinforced, single layer geogrid, 2-layer geogrid, and the geocell reinforced case. So if you look into these numerical models, we have considered the subsoil profile also. If you look into this chunk of the soil, which is 15 meter by 15 meter by 10 meter deep, whereas our foundation bed was only 3 meter deep, sorry, 1.2 meter deep. So that means we have even considered the subsoil profile in the numerical simulation to get the accurate result. So one of the challenge of this numerical model was for the geocell reinforced case, because it has a honeycomb shape, it's a 3D shape. Modeling that actual shape itself is a challenge. So with all the difficulty, we could able to develop this numerical model to get that mechanism of the vibration isolation. So whenever we go for the numerical modeling, various biggest challenge in this is that the determination of the input parameters. So depending on the constitutive model we select, these input parameters vary. In our case, more Coulomb was used for simulating the soil, and geosynthetics can be easily modeled using the linear elastic model. So for that, we have determined all the input parameters in the laboratory. Interface plays a very prominent role. For that, direct shear test, modified direct shear test was conducted on the soil geosynthetic interface. Then tensile test can be conducted for determining the modulus of the geosynthetic material. Similarly, this modulus of the soil can be determined using simple CU triaxial test. So this was the subsoil profile in that location where we have conducted the testing. So same subsoil profile was considered in the modeling, including all these parameters were taken from the soil report. And these are the material properties we have considered in the simulation. I don't want to get into the details of the material properties, but I want to show some of the results. The first step in the numerical simulation is always to validate with some of the existing literature from the experimental study. So in our case also, we have validated our numerical model with the experimental results. So here, basically, all the 4 cases we have compared the experimental results with the numerical results. And once the model is tuned to behave as a experimental results, then we have used that numerical model for further evaluation. So I want to show these interesting contours, which was developed from the modeling.
I hope that I can try to conclude.
Yes, I take just 2 minutes from here on. Yes. So if you look into these contours, like in the unreinforced case, we can see the vibration is spreading, to a larger zone. Okay. And the last case I want to draw, it is for the geocell reinforced case. Here, the vibration was basically confined to a very narrow zone. If you compare with the first figure. And this is the advantage, when you use the geocell, the vibrations will confine to a narrow zone. And in order to understand where this vibration is going, then if it is confined to narrow zone, if you take a section somewhere here, we can get this kind of image from the 3D numerical simulation. So this is for the unreinforced case, somewhere around frequency of 30 Hertz. And the other one is for the geocell reinforced case. So in case of geocell, I told it is confined to narrow zone. So if you take the section, we'll understand what happens is that under this vibration source, the geocell will act as a medium for diffraction. It will basically diffract the incoming vibration and it will allow it to pass it to a deeper soil stratum. So the vibrations are basically moving downward, not in the lateral direction. Okay, which is not moving in the lateral direction, we can basically protect the structure which is situated very near to the vibration source. So we could measure the strain in the soil because strains play an important role, which tells us whether the foundation bed is undergoing any failure. In case of the vibration, we could not see any failure. In case of geosynthetic reinforced case, I don't want to get too much into details here. And this is the last slide before I conclude. So here we have also noted down or measured the strain on the geocell, okay, or the geosynthetics. So because generally geosynthetics will fail when the strain level reaches around 2%. So if you develop an isolation system, but geosynthetics fail under the particular vibration, then that system has no use. But if you measure the strain in the geosynthetic, under the vibration of different frequency from 5 Hertz to almost 35 Hertz, the strain values are around 0.6% to 0.7%. So what it indicates that these materials will not undergo failure under this vibration. So this can absorb the vibration, but still will not undergo any sort of failure. So in a way, we got a concluding evidence that geosynthetics can be potentially used as a isolation material for absorbing the vibration. And what happens is that the lateral spreading of the vibration can be substantially reduced using this geosynthetics. So out of the tested geosynthetics, geocells found out to be the better option. And as I told before, this kind of system can be used for isolating the vibrations of machine foundations, railway, and pavement related vibrations. So with that, I conclude. Thank you very much. I apologize for the chair that I took a couple of extra minutes. Over to you. Thank you.
Thank you so much, Prof. Amarnath. Indeed, a very comprehensive, a very thorough study here. I think they shared quite a fair bit of details here, which I mean the extension of the time, I think it's more than worthwhile for all of us to be able to hear what that you have to share. Indeed, very refreshing to actually to see how geosynthetics able to offer that absorption, that mitigation of of the seismic impact on foundations. So as you can see from the chat window, that you have tons of questions. I know that time is not on our side, so probably I'll just pick just a couple of questions. So the first one that I would like to convey is what is the range of vibrations this can extend? Yeah. So, and also to what extent can this be used against seismic loadings on structures? And if this fails once on loading, how much residual vibration isolation can this provide? I think this is pertaining to the geosynthetic that you were sharing earlier on.
Yes. So as long as the intensity of the vibration is considered, this we have tested up to 50 hertz and peak particle velocity in the range of 17 to 18 mm per second. So under that vibration we have tested, because experimentally we cannot go beyond that, because there was nearby structures also. By extent we go beyond 50 hertz, our own building starts giving the cracks. So for that purpose, we have limited our study to 50 hertz and peak particle velocity in the range of 20. And the second question may be an earthquake related thing. Maybe Dr. Shion is the better expert. In the morning, he spoke nicely about resonance due to earthquakes and all. So I may pardon from that particular question.
Well, feel free to answer. I mean, no harm. There's another question. Do you think the Joule cells distributed the vibration to a larger area due to which is the efficiency has increased with the cells? Yeah, this is something that I'm also quite interested to find out from your insight, your understanding that what is the Joule cell actually doing, to
Yes.
the vibrations. Yeah.
Yes. So what we found from our 3D modeling is that when we take the sections at a particular level, so whenever vibration hits the ground, geosynthetics or geocells are placed at a very shallow depth. They sort of they will diffract. It will diffract the incoming waves, and somehow it will divert it into a deeper direction, not allowing it to laterally spread. So by virtue of that, vibration transfer deeper into the soil, not in the lateral direction. I can say diffraction.
Okay.
Yeah.
Interesting. Yes. Yes. Okay. Yeah. So with that, due to time limitation, so thank you so much for your sharing of the experiments and your thoughts. So I hope that that you can spend some time to answer the rest of the questions after your talk at your own time. While I will move on to the next presenter.
Yeah, sure. Thank you. I'll do that.
Thank you.